When I first met Tiwade, he was head of strategy in one of the large mining groups in the country. He really is educated in the US, Southern Africa. I think you did your MBA in the US, Tiwade, if I'm not mistaken, and but stays in Pretoria and has been doing a lot of work in the technology side of things. And where this started was about a year and a half, possibly even 2 years ago. I was discussing with Tiwade a challenge that he had with a project where he was successfully implementing, and I think if I understand it correctly, an Internet of Things solution in the water treatment plant of one of the local municipalities, and just found that it was difficult to get it going from there. So some success and some demonstrated success of the work that you'd done. You also, about 6 or 7 years ago, you presented to one of the Schedule 3As in the country on asset management. At the time, also, you were doing a lot of work in the early stages of digital twins. You've progressed that further. You've done some work in one of the large SOCs in the country. And really pleased that you've joined us today. So we're going to ask you if you can just kick off, just taking us through some of the digital twin Internet of Things in action in Southern Africa, and just show us that this is real. And then we're going to open up the discussion to talk about the procurement of those solutions and what that means. Thanks, Tiwade. Thanks for joining us.
Okay, thank you, Sean, and thank you everyone for joining us. Yeah, so the discussion is going to be largely a presentation, but I'll also do some demos. Now, sometimes the technology doesn't always cooperate, so if that doesn't work, then we'll just do the PowerPoint of those demos or actual solutions that we've implemented. So we may jump back and forth between the presentation and demos, and even the presentation itself back and forth, just make sure that we have a context.
Thanks.
So in terms of where we are going to go, we're going to do some definitions, and then we will touch on IoT and real-time asset health, digital twins, some case studies and demos. And then on the procurement processes and those sort of things, it will be more of a discussion than a presentation. There's only really one slide on that. And then maybe after that, we can discuss next steps. So a lot has been said over the last few years about the fourth industrial revolution, which blurs the lines between physical, digital, and biological spheres. And it integrates cyber physical systems, the Internet of Things, big data, computing, robotics. And these days, I think, what do they say? Every man and his dog, every man and woman and their dogs are doing AI, right? If you're not doing AI, so everybody's talking AI, but sometimes it's not very clear, but it is actually having quite a big impact. And then they say compared to previous industrial revolutions, this one is actually evolving at an exponential rather than a linear pace, with potentially significant impact on work, services, education, leisure, etc. The most profound change over the past 2,000 years. And I can attest to that. Just some of the things that we are seeing, especially on the AI space, is quite scary, especially the pace at which these things are changing and impacting lives. So if we look at more of what I'm going to be focusing on is on the technology side of things. So previously we had operating technology in the plants, and with IT as separate sort of fields. But what we're seeing now over the years, especially today, is that there's a blurring really and an overlap currently between operating technology and information technology. Currently, it's all just technology. You can't really separate the hardware, the firmware, the software. Everything is integrated, and which makes things much easier, and especially with cloud computing. the technology that used to be available only for large sort of corporates with deep pockets is actually available literally for small companies, and literally anyone on the planet has the same access to the technology that is available in the advanced world. So that's what's making this very effective. I mean, even the collaboration around the world. I mean, some of the projects that we have been able to do, we could collaborate with somebody in Vietnam who had never met, and don't think I'll ever meet. But it's actually quite interesting, but also makes it very powerful. So in terms of some of my examples are more in industry as well. So I mean, we work a lot in mining space. So the idea really is, and this can apply to any other operation really, looking at, in this case, the mining value chain from on the left-hand side, from the geology, and then the mining itself, and then the processing, the logistics, and the marketing. Right now, everything should be connected digitally and should be available on one platform in real time. And that's what's making it exciting, that we can actually do these things. And the technology that we will be talking about today actually enables this, and I'll be able to share with you some case studies around these sort of things. And this is an example again of someone in a plant. The idea here really is it's now an expected, not a nice to have, that if I'm walking around a plant or a factory, I should have all the information on my fingertips, whether it's the schematics, the engineering drawings, the inspection forms, the videos on training, if I'm not understanding how it works, the failure modes, the real-time performance, alerts and alarms, any safety videos, everything must be available on the fingertips, on my tablet, on my cell phone. And that's what the technology really, in terms of Internet of Things and the digital twin, and we'll talk a lot about smart sensors as well, because obviously for you to get this information, you need the sensors that are in the hardware that's actually physically installed that will transmit that information, and we'll touch a bit about that. So jumping on to digital twins, I think this is one of those things again, which is sometimes not easy to explain, and sometimes it's just a buzzword, and people might even say, why do we need them? So this particular example that I'm going to be sharing with you is actually some work that we've done on some thermal power stations in the region. So if you look on your left, a digital twin, really what it is there's a physical asset, which is in this case a power station boiler. And it's always amazing. We sometimes drive past these power stations and we can see them at a distance, but that entire structure you're seeing on your right-hand side there is actually 110 meters high and about 40 by 40 meters wide. So they are huge. So the idea really, and it's complex in terms of if you think about, and you see when I show you the sort of 3D model of these things, there's lots of tubing inside, literally 600 kilometers of tubes inside, and there's mills, and there's pumps, and there's a lot of physical hardware, which is complex to understand. I mean, just walking up and down, it is going to take you a day to just tour one of these. So what we do is the idea is we create a digital replica of that physical image, on the one on the left-hand side here. So you literally have the physical, a digital replica of that on your desk and then on your tablet and everything, which you can actually then see and you can interact with. And then on the extreme right-hand side here, we make sure that we have define what domain it is. Is it for simulation? Is it for function monitoring? Is it for predictive analytics? And we define the capability and we define the life cycle of that digital twin. What's important with the digital twin is that we can play around with the digital side without damaging anything. We can simulate. Once we're happy with the results, we can feed them back to the left-hand side. So this one here is maybe a bit more detail about what a digital twin is and what it does. We have again, on the right-hand side, the counterpart, which is the physical source, which is actually the one that has the data. We do what we call a physical to digital transformation on top here. We synchronize that with our digital twin. And here on the orange oval, we have we have what we call a data-driven digital model. We also have a physical or physics-driven digital model. So there are two types of digital twins. One is data-driven, where we're actually using the data from the physical device or the item that we're monitoring or modeling. We take physical data from there and we create what is called a digital shadow. So we shadow what's happening and we can see what's going on. Where it becomes a digital twin is where we play around with the physics. So we now derive physics equations. These are regression equations. These are predictive analytics, a lot of complex computation to say, okay, if for instance, if you take a power station boiler is affected by the quality of the core, okay, what physics in the quality affects it, or is the quality of the water? What physics? If it's the temperature, is it the creep? How does temperature affect? So we derive equations which enable us to say, okay, what if we are running the boiler at 10 degrees above its normal rating? What's the impact on the life of the tube? So it helps us then to feed back that information on the bottom here to the left, back to the left. So that's basically what the digital twin does. It's a very powerful thing, especially where it's very difficult to go in and monitor. So you can imagine something like a power station boiler. It's 1,600 degrees Celsius in there. It's supposed to run for 18 months without being opened. So you can't go there and monitor and do maintenance for 18 months. So you basically want to be able to simulate what it's like inside and then feed back the information so that when you do take it out, you have already predicted what's going to happen to this system over the next 18 months so that it doesn't fail in between and then you have load shedding or something. So in terms of the stages, we start with a digital shadow, and then we do the data-driven model, and then we do the physics-driven model because it's more complex. And then we typically have different types of, and there are many models, similarity models, where we look at previous run-to-fail data. We can look at non-threshold. We can then use degradation models, and I'll show you some of that just now to try and predict what's going to happen in the future. And then we can also use lifetime data and use survival models. There's a lot of models around this. That's three that I've chosen, but they're quite powerful in terms of being able to be replicas or producing replicas of the digital. So when we talk about remaining useful life, so for instance, we can track thousands and thousands of data points, which is where the sensors come in. Without this information, if we are still writing things in Excel, by the way, is not not digital. Here we're talking about, or even manual sort of measurements are not good enough. We need this information coming in real time so that we can collect a lot of this. So what you can see in these light blue lines are all the data points from the equipment that we are monitoring currently and or similar equipment. Out of all that, this is a data-driven model. So we then predict, so we can see our current model is the dark red here. We can now see that it is actually trending in that fashion. And at that point there, we can actually predict it's going to fail in 150 days. Then we do something about it, or we take decisive action, or we take evasive action. So that's kind of how we use the data and how we use the regression models to predict what's going to happen. I mentioned earlier on the issue of sensors. So again, here we've implemented, in our case, technologies like IP-based technology, which has hardware, smart sensors. It has gateways. The gateways are what communicate with the cloud. So we do get the information from the sensors, communicate to the cloud. But we also have machine learning algorithms that play within this technology. When we look at the actual sensors themselves, particularly smart sensors, they've got multi sensors in them. Typically vibration sensing, temperature sensing, and as well as in ultrasound, etc., in one sensor. You can mount it using a stud, you can glue it on, and also even magnetic mounting. And what's important here on the left-hand side is edge computing. So these are smart devices. It's actually a little computer sitting there on the bearing or on a pump, and it actually is doing quite a lot of computing on its own because of what we call edge computing. Doesn't need another set of computers to compute. It computes and then sends information directly to the users. Either via cloud. We ourselves use a Microsoft Azure IoT Hub so that we can actually look at this information from anywhere on the planet, really. We can communicate with the devices and you can remotely monitor and also you can have over the air updates. So that's basically it in terms of the summary and the background. I'll just then jump into the digital twins as well as a case study of a municipal, so digital twin of a power station and a pump station. And then we can also look at another example of AI-powered code of practice in real life. So in terms of one of the digital twins that we piloted was on thermal power stations. So these are very complex, and as we know, when they fail, we all are affected in the country because of load shedding and things like that. But they say if you want to go duck hunting, you must go where the ducks are. So 37% of all the outages are actually due to boiler tube leaks, and it's a very complex, very difficult thing to solve. As I mentioned earlier on, inside the boiler, it's 1600 degrees Celsius. You can't really go in there to do much for 18 months. So you need to make sure that whatever you do can last 18 months. And review of failure data suggested that if we can tackle that difficult problem, then it will have the most benefits because 70% of all tube failures result in outages. Therefore, if we can have an early warning system and an early detection, we can sort of help enhance the reliability. So this here is an example of the circuits in the boiler. So each of these are different circuits. And as I said, there's like 600 kilometers. These are tubes of inside the boiler on the top side of the boiler. The idea here is to have it color coded in such a way that we can predict. So for instance, if our prediction says it's going to fail within the next 18 months, then it's red. If it's going to fail within the next 54 months, then it's yellow. The next 72 months, it's green. And then if it's blue, don't worry, it's going to last another 6 years. So literally based on the conditions inside, we're able to predict and color code in such a way that you can clinically go in and say, okay, at this point on the right-hand corner, that specific point is going to fail in the next 12 months. Therefore, go in and do something about it now before it fails. And the idea obviously here is if you look at what I called earlier on a data-driven model, we look at maybe the last 3 years of data. We put a regression model, which is, so the light blue on the left-hand side is the actual, and then on the right-hand side, so all these lines represent a specific measurement point. And in a typical boiler, there's like 12,000 of these measurement points. So I'm just showing you a small sample. So here we can then predict that this one here is fine, but this dotted line here at the bottom is the ultimate tensile stress. So meaning when the thickness of the tube, which starts here on the left-hand side, I'm showing the thickness of the initial thickness of the tube, is going to degrade until if it reaches that point, which is 3 millimeters, it's likely to burst and then cause a failure. So we're predicting here when is each of these points going to reach that ultimate tensile strength where it's likely to fail. So in this case, so for instance, we started in 2022, we predict, okay, this is going to fail in 2025. Okay. So before you get there, do something about it. So I'll now go in and just show you an actual example of I'll try and demonstrate an actual case study. So this is a typical example. So if you look at a power station, it has maybe 6 boilers, and a color coding here just shows the actual state. So if it's in the red, means there's gonna be failure in the next 18 months. So you need to do something about it. And then if I just click on hopefully my internet connection works here. Okay. Sorry, it's gonna be a bit slow. Okay. So I click on that boiler, which I can see is in the red. In here, I can see more details. There's the different circuits. There's an economizer, there's reheaters, there's superheaters. And each of these, again, it shows that the economizer is in the red, the reheater 2 is in the red, the superheater is in the orange, the reheater 1 is in the green. So these circuits are fine. And this here summarizes the total condition of those tubes and their condition. And down here is a summary of, again, the same data as to when you must go in and cut it. But if I just show you briefly, when we say it is quite complex, so this is that whole structure I said, all the boiler tubes. This represent the entire tube bundles. And this structure from top to bottom is 110 meters high. But it's not just, when you zoom in, you can actually see that these are tube circuits, right? It's not just a mesh. These are tubes, for instance, that are spiraling from top to bottom. And then if you look at if you want to look in more detail on the upper levels here, you can actually see that, again, these circuits are quite complex, and you can play around with it and literally as if you are in the boiler itself, and see you can see how complex these circuits are. So when any of these points can fail, okay, so you can go in and zoom in and look at each of those circuits. Now, if I then want to zoom into if I want to zoom into for instance, the top one, which is the economizer, this helps, guys, because typically for maintenance personnel, it's very difficult for them to actually have a full view of everything. But with this, it allows them, again, I can zoom into one of the circuits. So now I'm zooming into the economizer, and I can now go into a lot more detail to see what's happening to my economizer. And each of those circuits there, as I said earlier, is actually not just, sorry, my mouse is too sensitive here. I just wanted to show you that each of these is actually a numbered area where you can go in and actually see the number there. I don't know if it's visual, but anyway, you can see what I'm saying, that you can actually go in. If each of those areas is color-coded red, it means there's something in there that's going to fail. It's an automatic indication that I can see that in this boiler, there's one point which is in the red, somewhere in the green, but I can go in and actually physically look. So this is very complex, as you can see, to try and go in there and figure out what's going on. And if one of these tubes in the middle fails, typically how you would repair, you'd cut everything from the top to bottom, get to the bottom one, weld it, fix it up again. That's why the outage takes quite a long time, and it's very expensive, costing us billions and billions of rands. So in this case, we're able to actually build these models and see virtually and in real time actually what's going on these elements. And if I can double click into that bundle, I can now go into that prediction model that I was saying earlier on, because I can now actually see what's happening. Each of these is a measurement point, and I can see when it's going to cross the cut line, when it's going to fail. And then I can even still more detail go into each of those and see. Again, I won't necessarily go with a lot of details, but we can go into each of the circuits and see what's happening. Each of the elements, actual measurements. So you can drill down and see. So this is an example of when these colors are being, this is now element by element. Each of these things, there's 192 tubes across, and there's a lot of detail. So again, I don't want to bore you with the sort of details there. I hope that makes sense in terms of what that means. If I go into the next case study is on the municipalities. So this is a municipality smart water system. Again, things of service water delivery. We've been hearing a lot about water. There's now even the president is focused on the water or supply situation in the country. So we did some work with a municipality in terms of making sure that the assets are reliable, the smart water. I mean, just the issue of non-revenue water is massive. I mean, some municipalities, as much as 40 to 50% of the water is unaccounted for. And so with smart technologies, we're actually able to assist with that in terms of monitoring the condition of the equipment, the pumps, the pipes, and also detecting, where those water losses are happening, and to make sure that at least we enhance the water supply reliability and even quality. We're able to, with smart sensors, measure in real time the quality of the water. Because I mean, the municipality we worked with, they even said, you know what, we sort of test our water at the pump station, it's okay. But somebody down the road there, a kilometer or 2 kilometers from the pump station, they're complaining that there's E. coli in the water. Meantime, that's because somewhere along the line there's a sewage pipe that's burst, and there's also the water line that's burst, and the two mix, and you end up with the sewage at the end of the line. So we can kind of detect even within the dams themselves. But what I'm going to be sharing with you now is in the pump station. You can see that was our team there doing the installations. And maybe before I jump in, I can just show you. Okay, we did those pumps, tanks, and those sort of things. But then maybe I can share with you before I jump in. Maybe let me go back and show you briefly. How do I get to this here? Again, the ability we have with the technology is to make it real. So this is the actual pump station, and you can literally walk in the pump station as if you are there, right? You can swing in, you can walk back and forth. You can see the condition. So if I zoom on to that one, I can see the details of that pump. I can see what's happening to this pump specifically, what's happening with that bearing, what's happening to that. And I can get this transmitted to me directly wherever I am. So I don't have to be at the pump station to see. I can walk up and down the stairs. It's almost like I'm there. I mean, literally better than the guy who is there. So that's the power of doing these sort of 3D models, and it makes it real. It's not. Again, I won't spend a lot of time on that. Maybe I can go back to the sort of things you are then able to do. That's the same picture that I showed you earlier, but we can do alarms 24/7, 3D reality with a SCADA view, and there we utilized accurate smart sensors, condition monitoring, gateways, 3D visualization, alerts and alarms. And again, that's the 3D model I've just shown you. These are sort of the dashboards that you can get literally on your laptop or on your cell phone, wherever, with alarms, a lot of detail that you can get, lots of diagnostics around what's going on. Okay, so that's just the okay. The next case study is not really a case study; it's an example of AI-powered code of practice. So in terms of safety, and in a lot of mines, we work in a lot of mines. There's a lot of incidents where, in most cases, invariably, it's about a code of practice or a safety practice that hasn't been adhered to. With AI, we are able to actually assist. These days, I am amazed. Even every other vehicle coming on the on the market is some intelligence. Some of those new vehicles now, it's very difficult to crash them, because I mean, it tells you, you are about to cross the line in the middle of the road, or there's a car coming, or you're about to bump into something. So there's a lot of technology already that's out there. We just need to put that in our working environment. And so here we can digitize work procedures, make sure that the work is done right, done safely. And also with the staff turnover, we've lost a lot of corporate memory. I mean, I was amazed listening to the radio driving yesterday, when the city of Cape Town had to bring in 62 retired um, people to just get back that corporate memory that left when those guys retired. But with digitalization and AI, we're able to actually get that corporate memory and make sure that it's available to safeguard that, especially when it comes to safety. So we need to embed procedures into AI-driven procedures and link them to performance and link them to how specific tasks are being implemented. So as an example, I don't know, Sean, whether does this sound come through when I play? If I play a video?
It only if you shared with sound, then we will.
Okay, maybe let me go back.
If you want to unshare and then share with sound, then it would work.
Okay.
There seems to be a problem with the lights.
Ashok, can you hear the sound?
Yeah, perfect.
Okay.
Job started.
Directions.
Walk 50 feet, then turn right.
Waiting to hear if there's a problem.
Warning, confined space. Panel located. Enter code 72. Initiate relay. Disable active circuits. Disconnect cable. Remove unit.
We've been told the problem with the lights is being fixed. And there they are. The lights are back on.
Call Phil.
Calling Phil.
Yeah, this doesn't seem quite right.
Let me take a look. I'll take you through it. Hit the relay button,
Okay.
then 784.
Got it.
Yeah, it doesn't seem quite right, but it'll be okay for now.
I'll put it in work order in for next week, Phil. Thanks for your help.
New work order submitted.
Okay. So yeah, and again, these things are available. So maybe in conclusion, the technology IoT digital twins will have a big impact. And obviously the way to actually implement these things initially, we will typically do an initial assessment of the requirements. We have to have a clear definition of the problem that we're trying to solve. And typically that the next step will be to do demos so that people can see in real life what's happening. Then in most cases would need a proof of concept as well to make sure that this actually the technology will work in that environment. And then you pilot the technology, and then you implement. So for instance, that point that I showed you on the municipality, we did the pilot, and Salga was saying, okay, now what do? We need to scale this up to the rest of the municipalities, for instance. So that will be an interesting case if that works. But the pilot site worked, and then we obviously need to roll it out to a number of the other pump stations. Okay, so the next step is about just a discussion. I think Sean will probably lead the discussion in terms of implications for procurement processes. Thanks, Sean.
Well, thank you very much, TNT, and fascinating. Thank you for sharing that. I guess that last video that you shared can be done now. I mean, that's not some futuristic thing. It's doable now.
Yeah, absolutely. I mean, if you've ever played around with AI now, we were having this discussion with the developers in our teams. I mean, just as an example, another aside. So we wanted to develop a piece of software. And the team had already been busy with this piece of software for 4 months, a team of developers. So I said with one of my colleagues in the UK, he's working in the banking sector there. He says, no, let me show you how you can do this. I tell you, in 30 minutes, we had a working minimum viable project. The guys, the team had been busy for 4 months. We were able to have a working model in 30 minutes using artificial intelligence. So it's quite scary, actually, to say the least. It's quite very powerful. Yeah.
Fascinating. So TNT, these are in some ways, complex solutions. They're not necessarily off-the-shelf solutions where you can go and you can buy something and say, "This is it. Let's implement it. It's in. Let's go." And that's why in the previous slide you had different steps that you discussed. You could go back to that slide. You mentioned there's an assessment, there's an evaluation of requirements, there's demonstrations, there's proof of concepts, there's pilots, there's various things like that before you can actually start implementing. So our procurement system that we've got, in simplistic terms, says the following. It says, organ of state, put together a detailed specification. And that must be, and I'm going to use a word, precise. Put a precise specification together, send it out to the bidders. The bidders will then respond with a solution and a priced solution. And then we basically ensure that we can tick all the boxes in terms of the functionality. So they've got sensors, they've got the dashboard, they've got all these things, tick, 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 tick. Yes, it's an acceptable solution. And then we award on the basis of price. That's not that easy with this, right? I mean, if there was an organ of state now in a municipality and they said, Tiwode, come along or anybody, come along and put in place a monitoring solution for our water plant that does all the stuff that you had there in Carolina. Can you put a specification together and price it and give it to them? Difficult.
Yeah, I think it'll be difficult because you'd have to go there and do the assessment, as I said, evaluate, ensure that you've seen the pump sizes are very different. I mean, if you just look at a municipality pump station versus a water supplier, like, the bigger ones like groundwater or those sort of things, their pumps are much bigger. So you can't really say, okay, what will work for a groundwater might work for a municipality, for instance. So it would, you'd have to obviously go there and get the details and then pilot, yeah.
And then pilot. No, but we can't do that, TNT. We're looking for a priced solution. I'm teasing you now because that's what our procurement system requires, right? The procurement system requires that we put a precise specification together. We send that out, and you give us a price to do it. But you can only do that if you can get in there and have a look and evaluate and do an assessment. Figure out. Let's take the sensors. Are those sensors ready to go, or do you need to?
The sensors are ready to go.
Do you need to
the technology is there,
or tell them what to do?
Yeah. So the sensors are ready to go. I mean, they can pretty much work in a lot of places. So the hardware is fairly straightforward. I mean, the hardware is available and it can go. Yeah.
But do you not have to configure the hardware? Do you not have to say this particular sensor needs to look at vibration, and that you calibrate it then, and you tell it when it gets to this level, it must issue an alarm, and do you not have to do some work on it, or is it just can you issue it and the guy in the municipality can just go and plug it onto the machine and it'll do the job? I imagine there's some work that needs to be done.
Yeah. So there again, yeah. So every piece of equipment is again different. If it's on a ball mill, or if it's on a pump, or it's on a compressor, it may be the same sensor, but it needs to be configured for that specific piece of equipment. So it's not exactly gonna be okay. I bought it and I'm just gonna fit it in. You'd have to do those calibrations and setting all those alarms. Yes.
To say this is when it gets to this level of vibration, then you need to trigger the alarm, and that's going to take some work, I guess, to do that. It's
Yes.
okay, and then the other issues around we're gonna come into construction, and now I see Mike has put his hand up, and then when we come to the digital twin aspect, I mean, the dashboard that you put together there, certainly that probably requires some coding, that needs some work to be done to make it real. You need to interface it then with all these devices that are out there. You possibly need to interface it with all the operating solutions, I think, or the operating technology you mentioned in one of your early slides. There's probably a whole bunch of integration work that needs to be done as well. And it's not easy to estimate that unless you can get in there and have a look.
Yes, yeah. So again, with the digital twins, as I said, a lot of the work is actually in preparation than the actual stuff. You have to go in there, understand what's physically available there now and what needs to be added, how they work, and then devise, sort of the physics around them, and even if you're going to, like I showed you doing the 3D scans or the 3D drawing, so that you can visualize everything in 3 dimensions. There'll be a lot of just because it has to be real. It can't be just some other look-alike, because it has to be literally identical to the item that you are trying to measure. Otherwise, you're going to be showing false information. So yes, there's a lot of work to do to prepare and to work with that. So remember that I said, that's what I said earlier on when we were just doing that pilot project. It was a multidisciplinary, even multinational sort of team of people that we were to go and source some specialized skills from Vietnam that we found there, and the guy had to help us with some stuff and all that stuff. So just to do the initial proof of concept, before even we do a pilot, then we say, okay, this model works. Now let's scale it up to a pilot. And then after the pilot, then we can then scale to the full thing.
One of the difficulties, and was that a project that you did where you invested yourself, or were you paid for that?
No, with all these proof of concepts, it's an investment on our side. And then
investment on your side.
Yes, yeah.
And then one of the procurement challenges that we then have is, well, okay, TNT, you've done this work and you've put this proof of concept together, and now, Carol, great question. And now, we've got the specification, but Tiwade, you put the specification together. We can't now invite you because you put the spec together. So we've got to invite other people now because you influence the specification challenge. And I'm wondering if that isn't the reason why nothing moved forward in your Mpumalanga case study.
Yeah, possibly. I mean, it is a real challenge because of the governance issues there. Yeah, the other bidders will say, well, this guy here, this company here had an unfair advantage. So it is a dilemma, yes. Yeah, that needs to be resolved.
Yeah. Just a last quick question before we go to the comments in the chat, and also give Mike a chance. I saw Quest. You had the sensors there. Are you is that an international product that you guys are the agents of, or where does that product come from?
Yeah.
The,
Yeah, so
the
iQuest
sensors.
is iQuest is our technology partner. We partnered with a company in the UK that actually does that. So we co-develop these technologies with them. But iQuest Technology is actually a UK company which we have partnered with. So we with our own team in there and their own teams in there, and then they are developing technologies, because some of these technologies are actually new, and it's not like you can just go and buy off the shelf.
Mm.
So, but the hardware, some of it you can buy off the shelf, but a lot of the technologies we co-developing with them, and they're developing it as well.
Mm.
And then we distribute the technology.
Thanks, Tiwade. Let's jump to Mike. And Mike, let me just be sure that you can unmute. Yes, you can. Go ahead.
Sean, regarding your procurement, I can only talk about engineering works and infrastructure. There is provision in the CIDB standard for uniformity for using the FIDIC Yellow Book, which is a build, operate, and transfer. So something like this would be ideally suited to that type of an agreement. In other words, a private party builds, provides the infrastructure, gets paid by whoever is using the resource that they provide, and they manage it. And then they transfer the technology, the knowledge, the training to the municipality or the public entity. It's been done a few times with water, but it was unsuccessful because of the usual political interference. Now we're in a situation where the majority of municipalities are with their backs to the wall and they don't have much choice. If they want to provide water, they need to do it with the companies, because they don't have the assets, they don't have the capacity, they don't have the knowledge, they don't have the expertise to actually manage these systems properly. I mean, you can see in Johannesburg, it's quite obvious. You know, when you're without water for a month, it means that whoever's supposed to provide you with water doesn't know what they're doing. So build, operate, and transfer contracts are ideal for this sort of thing, where the bot contractor buys water from the large supplier, could be Rand Water, and then distributes it. So it's in the interest of the bot contractor to minimize losses, because those losses cannot be built into the tariffs. So you end up with a situation where you transfer all the risks. You obviously pay a price for it, but ideally you end up in a situation where when the assets are transferred back to you, they're in good working conditions.
Got you.
I mean, it's a fact.
Got you.
It's a PPP, but it's a form of a PPP, but I mean, the state cannot provide some of these things, and one must just wake up to the realities of life. You're either without water and you accept the status quo, or you find a different type of solution. And beating the same drum, expecting a different tune isn't going to work. And I mean, it's been shown over and over and over. So, this is part of the innovation process.
Did you hear the president's speech? And
politicians. I'm a technocrat.
To bring in private sector to help with the water plants, and he didn't say that, but yeah.
But Sean, the idea of bringing the private sector is to build new plants. It's pointless building new plants when you lose 40% or 50% of what the new plant provides. It's actually crazy.
Thanks, Mike. Yeah. Good one. Thank you.
Wasting money. Yeah.
Thanks. Tiwade, just checking if you can see the chat. There's a question from Carol. What is the typical timeline for digital twin? And Angelo is asking what FMECA approach was adopted for existing infrastructure / equipment. So give that some thought. But I'm gonna ask Penelope to just come in first. Penelope. So you're saying, as with some construction, the pilot or proof of concept would equate to a feasibility study. It would therefore be a section of the total plant, so the procurement would be for a feasibility study. And so the question, Penelope, is once that you have done that feasibility study with the supplier, how do you then roll that out? Is that then subject to just a downstream project to take that forward, or is this something then that needs to go out and tender again for the rest of the site? Maybe Penelope, I don't know if you can come in and just talk to us about that. Hi, Penelope, there we can hear you.
Hi there. Well, in our environment, what we do, depending on the nature, how clear you are with the scope. So we've had some environments where there's a section of the operations which we cordon off, and we put the proof of concept there. And if it works, then so that team can now, depending on how the project manager has structured it, the team is actually appointed as the professional team for the project, and part of the scope of the professional team is to do a feasibility study, proof of concept, pilot site, whatever you want to call it, and then they continue with the rest of the project as the principal agent. So they will oversee the subcontractor that we also appoint, and they will do the rest of the plant. So the principal agent would effectively give direction, would say, look, here, this is the standard you got to adhere to. Sometimes, however, you find that the proof of concept proves to be not the right fit, or you find that the environment is not conducive, or you discover the cost are prohibitive. You then have a clause which you say, well, should that be the case, we will stop. So it gives you that flexibility, because a lot of technologies, when it comes to this sort of thing, it works in specific contexts. It works So that's how we typically do it. So we include the feasibility, and should it be, I mean, especially things that have been like gas to power, things that have been done before easily, those sort of things, we know where we're going. We understand what the outcome is going to be. So the professional team is procured to do the proof of concept at a small site and go forward with the project, and all of those things. It is a procurement, little bit of a tangle there, but you understand what you're going to do. Is that your principal team, the first group, is actually the leaders, the concept development, the guys who say, well, this is the blue sky idea. This is all that we can do, and we're going to narrow it down here for this site, that for that context, in that plant, like that. There was a mouth. Thanks.
And you're in public sector, Penelope?
Yes, I am.
Yeah, good. Thank you. Teore, any thoughts on timelines for a digital twin project?
It will take 6 to 18 months, depending on the complexity, to just get the first part going. Obviously, by the time we get the 6 months, we will have at least a proof of concept working, and then pilot from there. So within 6 to 18 months.
So proof of concept 6 months, and then from there it's going to depend on scale and size of the rest of the project, I guess.
Yes, yeah.
Angela's question: what FMECA approach was adopted for existing infrastructure equipment? Do you know what FMECA is, or must we ask Angela to explain it?
Well, assume, is it failure modes and effects and criticality analysis?
You got it.
Let's make sure we're on the same page. FMECA. So yes, so we are also, primarily a reliability company. So we, as part of the iQuest suite, we actually have and tactic development software that does the failure modes and defect analysis and criticality analysis. So yes, we would definitely have done that. Because we've shown you obviously, when you design what sensors to put in and what to monitor, everything there is driven by the failure modes that you're trying to arrest, so that you don't just go in there. We know typically, for instance, with the equipment, 80% or 89% actually of all the failures are pretty much random and unpredictable. And sending a technician, an artisan there every so often, every week, every month to check is not going to help reliability. So we then tackle those based on a very detailed failure mode and defect analysis and critical analysis.
Angelo, did that answer your question? You can.
Yes, in some degrees. I just want to understand but thanks for the presentation. It's well received. I just want to understand when you have a client with existing infrastructure, what approach would you adopt going in there? Because obviously now it's been a while that the infrastructure is there or the equipment, as opposed to new equipment. Just your thinking around it. Thanks.
Yeah. So in fact, almost all the clients we're working with now have had equipment in for a long time. The gold mines and those sort of guys have old equipment, and they've had a lot of equipment. So we initially go in and do an assessment, and we assess what sensors they have in the plant. If they have the PT100s, we did a sugar plant where they didn't have those, the analog sort of dial gauges for pressure and vacuum pressure and those sort of things. We would then recommend different sensors, or in this case, for the sugar plant, it was more digital vacuum pressures. So we would go in, and whatever is available, if it can be digitized, we digitize what's existing, and then we recommend the additional hardware to be put in. But we start off with what they have. Sometimes, because people seeing is believing, even if they have a few that we can sort of hook up to the system, the minute they see that live, then they can see it works. So if they have a few, we can start digitizing those, and then we recommend more in order to achieve the results.
Angelo?
Yes, thanks. Thanks, Ron.
Good on. Nomawetu, we're going to come to you now, but I'm just going to ask Chris to first come in. And Nomawetu, if you can just be ready to talk a little bit about that. Go ahead, Chris.
Thanks for a very interesting presentation. As someone in the water industry, it's certainly that pump station was really interesting. But to come back to the procurement rather than the technology itself, the Public Procurement Act now promotes innovation, and we're anxiously awaiting the regulations to see how we're actually going to procure innovation. Because this is definitely following on from last week's topic. This is very much a procurement of innovation. Going the triple P route, I think, will have some problems of its own. One of my colleagues, Rosanne, is in the audience today, and she's had experience also in trying to get triple Ps off the ground. And it's a very long, tedious process, even with the recent attempts to streamline it a bit. And the way that this technology is evolving, by the time you get a triple P off the ground, the technology will be obsolete already. So you're going to be almost back to square one. So this falls, I believe, more in the realm of unsolicited bids, whereby someone who has this technology could go to municipalities or organs of state and propose it as a unsolicited bid. Again, we'll have to see what the regulations, how they're actually going to deal with unsolicited bids, but that might be an option to get this thing going. It's going to be very difficult to put out, as Sean pointed out, some of the aspects of a formal tender. You've got to get pricing. How do you price something that you don't yet know what's actually going to happen? So yeah, that's just my thoughts on the matter.
Thanks, Chris. Nomawetu, let's just discuss your point. And this is precisely the issue. So you've said municipalities can invite all the potential customers to be part of drawing up the specification, to remove the element of biasness when it comes to the bidding process. Will that not work? So part of the challenge, and this is what I'm going to ask you, Nomawetu, is if you've got somebody that then has put the spec together, would you invite that company to bid for the work? Mamawetu, welcome. You've unmuted.
Hi, everybody. Yes, I was asking in terms of this digital twin concept that is coming into play, because now it seems like we are running in circles, and they are inviting the company who actually does the work, but at the same time, they don't want to invite them now to actually come and do the work. How is anything going to get done if we are running in circles like that? Is it not possible if we could actually get the companies that actually do this kind of work, collaborate, come together, and do the specification of drawing up the specification of what needs to be done, and then actually inviting them to come and bid and actually do the work, because they know how the work is supposed to be done. This is not done in isolation with the companies. It's done with the municipalities themselves. It's not as if they are sitting there doing the specifications all by themselves. This is done together. It's a collaboration between the municipalities and the companies, and then the best person will actually take the project on once the bidding process is over. That was my thinking around the whole thing.
So, I mean, this is the challenge, and so we need to come back to Chris's point. We need methods that allow us to appoint somebody who does a pilot or a proof of concept, but then is allowed to continue into the next phase. And one of the reasons of a proof of concept, it's not just to show, hey, this works. Tirole, help me here. It's not just to show, hey, this works, but it's also for the supplier to estimate, right? It's to say, how much work do I need in order to get to this point? And then to take it further. I hope I'm not losing connectivity. And then to take it further and to say, okay, now if I was to roll it out to the entire plant or the section of the plant, then this is the effort that it's going to take me to do that. And the proof of concept and the pilot certainly helps you better estimate that. Tirole? Okay, I'm back on.
We lost you there. We lost you there a bit. Can you hear me?
Back on. Thanks. So I was just saying, the proof of concept and the pilot is not just to say, hey, this works, but it's to better understand the effort that it's going to take to roll it out to the rest of the plant. So it gives you information, how much work is required in order for me to get to this point of the pilot. And I now have a better understanding of how much it will take now to finish the rest of the work. It's not just to show it. It's also to help to estimate the implementation. Just checking with you if that's the case.
Is that a question to me, or
I'm asking you. Tirole. It's not just, hey, this works. It's to provide you with information on what it's taken you to get to the point that you've got a working model, so that you can
that's right.
estimate the full cost of a full implementation.
That's correct. So I think in terms of the whether the technology works or not, I mean, there'll be a lot of places where the guys can just go and visit. I mean, so there's the technology works, but it's mostly because the environments are very different, and then you need to make sure that it can work in those environments. But maybe can I just add on maybe another, maybe it's a question as well as a potential solution. So with one of the gold mining companies, again, I think somebody asked about the old company. So this guy's an old gold mine, and they wanted to start the whole journey of process automation. And so what they did in that case was to invite potential technology partners, and they rather evaluated their capabilities or competencies within those companies, and then selected a company as a partner to say, okay, we're going to now go on a 5-year process automation journey. And we don't know what that entails. We will need you to come in and specify and quantify the work and provide the technology as we go forward. So the bid solicitation was to get it almost like an in-house team, but it's a partner. Then that becomes a technology partner that they then go with on that journey. So so that you kind of not necessarily. I don't know whether that can work in public sector.
As long as it's started with that intention, and that there's clear recognition that the cost of the entire project cannot be estimated with the first proposal.
Yes.
But there's going to be sections and different estimates and different costing that would go. You can't on the first proposal estimate the entire cost for the entire project.
Yes.
And currently, the procurement processes almost require that. I just need to quickly respond to something that Mike has raised. Mike, please do not take the Oricon City of Cape Town case as being we can now appoint somebody to do the feasibility study and the specification and then also do the work. It's far more complicated than that. So just watch that one. There are very specific clauses now in the SPD4s that clearly state that if you were part of the specification, you may not bid for the work. So it's got to be very, very clear. Please don't take that particular case. We did a bit of a deep dive on that Oricon one about a year or two ago. So maybe we need to revisit that again. Thanks, Chris, for your responses, and Tsepo as well. Okay. Thank you, Ture. That's we just asked you for an hour. We've gone past that. If there is anyone who would like some more information from you or would like to contact you, are you able to put your contact details in the chat?
Okay.
We don't often do this, have suppliers on, but this is quite a unique piece of work, and you've put together some fairly unique skills, and you've done quite a lot. You've already invested in a water plant in Carolina, a project there. I hope that at some point you can start to recoup the investment. But if you can just give us your contact details, I'm sure people will appreciate that. And otherwise, if there are no other questions, the purpose of today was not to say, okay, this is how you buy it. The purpose of today is to start to just raise the challenges that we have in the procurement process. And I think we've achieved that, and could not have done that without your support today. Thank you.
Okay, sure. No, thank you very much, Sean. I think it's a pleasure. I think it's always good to share, and to also, I think for me as well, it was an eye-opener to try just understand those complexities. It helped explain some of the challenges we faced with with public procurement. To just there's quite a lot behind that actually became clearer for me as well today.
Good one. Thank you. And well done to you for all the work that you're doing. Well done.
Thank you.